What if dark matter isn't a mysterious exotic substance, but a subtle consequence of the difference between gravitational and inertial mass? Today, we explore an unexpected perspective. By revising Einstein's energy relationships, Ozyak relativity halves rest energy, enabling negative temporal momentum without negative energy. This innovation reinterprets particle dynamics fundamentally. Harari and Shoup's Prion model reveals that quarks, leptons, and bosons are composite, reflecting near-equal matter and antimatter. This balance influences mass differences in surprising ways. Combining modified gravitational constants and distinct inertial measurements, the model predicts a dark-to-visible matter ratio near 6, derived from intricate Prion count and energy dynamics. Experimental approaches range from re-examining gravitational constant measurements to designing new tests. Variation with material composition could confirm this innovative model's predictions. In conclusion, rethinking dark matter through alternative relativity and Prion models challenges convention. Further experiments may revolutionize our understanding of cosmic mass.
The paper we're diving into today is Dark Matter as the Difference of Inertial and Gravitational Mass by David Lush.
Yeah, and wow, what a title, right? Dark matter as the difference of inertial and gravitational mass. It already hints this isn't your usual let's find a weird new particle approach.
Right. So the core problem Lush is addressing is the whole dark matter mystery. You know, galaxies spin way too fast to be held together by just the visible stuff. Stars, gas, dust. For decades we've wondered, what's this invisible, dark matter giving them their extra gravitational glue?
But here, Lush comes at it from a totally different angle. Instead of inventing new matter, he's basically saying, well, maybe the laws we use to add up mass, inertial versus gravitational mass, need a rethink. That's pretty wild, because, in physics class, weren't we taught those two are always equal?
Exactly, and that's key. So he's questioning something fundamental. Lush builds his argument by combining two unconventional theories. One is Osiak's tweak on special relativity, and the other is the Harari-Shoup model, which says that even the building blocks of matter, quarks and leptons, are made of even tinier things called prions.
Yeah, that prion thing is wild. In the Harari-Shoup model, every elementary particle is basically a combo of just a few types of prions and antiprions. So, at that level, matter and antimatter are thoroughly mixed together, which is not what we usually think.
Right. So, if you take that and then bring in Osiak's alternative relativity, which, among other things, apparently allows different ways of adding up energy and mass for composite systems, suddenly you can get situations where a lump of matter's gravitational mass, the amount it pulls gravitationally, is different from its inertial mass, the amount it resists being pushed.
Okay, so you're saying that in this hybrid theory, a hunk of matter might weigh more gravitationally than it weighs when you shake it or put it on a scale?
Exactly. And that might sound bizarre, but Lush argues that we only measure mass via inertia, or the weight in the local gravitational field. But if these quantities diverge because of this prion-antiprion mix, we could be underestimating the true gravitational mass of, say, a whole galaxy.
So under this model, when astronomers measure the mass of galaxies using stars' orbits, the numbers seem too low. But that's because they've been using the wrong version of mass all along?
That's the idea. If we've been equating inertial and gravitational mass, but in reality, gravitational mass is higher, then the so-called missing mass, the dark matter, is just this difference. It's not made of exotic new particles, it's baked into the fabric of what we already have.
One thing that fascinated me was that Lush even tries to estimate the ratio of dark to visible matter by tallying up prions and antiprions in a typical atom, like deuterium, and he ends up getting numbers that aren't far off the dark to visible matter ratios we see in observations, like 6:1.
It's definitely a hand-wavy calculation. He even admits that. But the fact that it lands in the same ballpark is, at the very least, pretty suggestive. But of course, these models aren't mainstream.
No, but it kind of gives you a different feel for what academic research means, right? Like, it's not that he's claiming absolute truth, it's more, here's a framework. Here's a way to see familiar problems from a new angle. And if it sparks an experiment or a new analysis, then awesome.
True, and he does mention possible ways to test it, like if you could somehow make highly precise gravitational constant measurements with test masses of radically different composition, you might see tiny differences. That would give a clue.
That reminds me of, I don't know, sort of like the early days of atomic models, when you know you're missing something, but you're not sure where the fudge factor is yet.
Or like when people first suggested the neutrino to explain missing energy in beta decay. At the time, maybe it seemed desperate. Now it's basic knowledge.
You know, I think I read somewhere that most dark matter searches have been looking for new particles, and, well, nothing so far. This paper offers a reality check. Maybe we're barking up the wrong tree?
Or at least, maybe we shouldn't rule out wild alternatives.
Welcome to In Depth with Academia. I'm Richard Price, CEO of academia.edu, and today, wow, do we have a fascinating and thought-provoking paper to discuss. We're diving into dark matter as the difference of inertial and gravitational mass. Yeah, you heard that right. The title might sound a bit dense, but trust me, this idea could change how you look at the universe. First, as always, I'm here to present this work neutrally. I'm not endorsing or debating, just sharing the author's perspective so you can ponder it yourself. Academic research is always evolving. Nothing is set in stone, right? This is our chance to explore and reflect. So let's start with the basics. The author is David Lush. His paper tackles one of the biggest mysteries in modern physics. What is dark matter? For decades, astronomers have realized galaxies rotate way too fast. If we only count the stars and gas we can actually see, there's got to be more mass out there, something invisible, hence dark matter. But here's the problem. After years of searching, physicists haven't actually detected any candidate dark matter particles. No definitive sign of these mysterious things. So what if we're looking at this all wrong? What if we don't need exotic new particles? David Lush's paper suggests an alternative. The core question, what if the gravitational mass of ordinary matter is actually bigger than its so-called inertial mass? And crucially, what if this difference is enough to account for all those galactic oddities? That's a wild idea, but let's break down what it means. Okay, pause for a second. Let's digress. You know, this reminds me of when I first tried to assemble my own IKEA bookshelf and realized halfway through that maybe I misunderstood the instructions. Sometimes, maybe the answer isn't to look for a missing piece under the sofa, but to look at the instructions from a new angle. Anyway, back to dark matter. So the paper draws on two not so mainstream ideas from theoretical physics. First, there's a proposed revision of special relativity by Osiak. It says basically that Einstein's equations for energy might not capture the whole picture. And the second idea, it's called the Harari-Shupe model, which proposes our quarks and leptons aren't truly fundamental, but made out of even smaller parts, preons. These are elementary particles, and they're antiparticles. Mix these two ideas, and you get something pretty unique. Here's the argument. If ordinary matter, what we, see every day, is actually a mix of matter and antimatter bound up tightly together, then its inertial mass, the property that resists acceleration, can be less than its gravitational mass, the thing that creates gravity. That's pretty wild. Okay, let's get concrete. Lush calculates for certain atoms like deuterium, basically heavy hydrogen, that the gravitational mass could be 7 times the inertial mass. Imagine you pick up a block of deuterium and weigh it or push on it. It behaves like it has mass x, but its gravitational pull on other objects, that could be 7 times greater. Suddenly, you don't need hidden dark matter. If every star and bit of gas is weighing more gravitationally than we expect, the observed galaxy rotations make sense. Now, method-wise, Lush takes the preon model and looks at the numbers, literally counting up preons and antipreons in atoms, asking how that composition leads to different mass behaviors under these new ideas. He checks how much extra gravitational pull arises from all this. The paper even refines the model, considers effects like quark-binding gluons, and explores if those account for any dark matter shortfall. Key finding, it's plausible, at least within this framework, that the dark to visible matter ratio matches observations, even if, the explanation is completely different from what mainstream physics assumes. So what does this mean for you, the listener? Well, if you're interested in science, it shows how radically new perspectives, sometimes controversial, sometimes even outlandish, can shake up old questions. It's a reminder that science is a process, a conversation, and that the search for truth is always open-ended. This paper isn't claiming to settle the dark matter debate, and I'm not claiming it does either, but it's a real example of academia's creativity. Let's wrap up. We talked about galactic rotation, alternative relativity, tiny building blocks called preons, and how the way we measure mass could be key to solving cosmic puzzles. No matter the outcome, the heart of research is opening our minds to the possible, trying out new ideas, and challenging what we thought we knew. So, thanks for tuning into In Depth with Academia. I'm Richard Price, presenting this research neutrally as always. I encourage you to read the paper, think for yourself, and keep questioning, because that's what academia is all about. Until next time, stay curious.